Well, it's 9:05 already. Okay, the third one. So, okay. Okay, so let's get started. Last time, okay, we finished the previous part, okay, such as like a comparing like a different groups, and then we move on to talk about the hierarchical model. Okay, I gave you some examples, and the one used in the textbook is the the water, okay, quality of the water, okay, and if you get like a sample from like a different area in a city, okay, for example, like we are in Zhongli, right? We are in Zhongli district, and apparently our neighbor district includes like Xinwu, Yangmei, and what else? Yeah, we have many districts in Taoyuan City. Okay, so say if we measure, if we sample like the water from like different places in different districts, our purpose is to measure the water quality of the Taoyuan City. But at the same time, okay, because the samples come from different districts, so it is inherently hierarchical. Okay, they are, the data itself, contains certain hierarchical information in it. Okay, this is very common. Okay, I think last week we also used like some example. For example, like like an NBA player. Okay, their performance. Okay, because NBA player. Okay, we know NBA is a league. Okay, but each league, the whole league has many teams. So players belong to, a specific team. Okay, so again, you can see a certain hierarchy in this, example. So a lot of time when you collect data and when the data, source, okay, has such a hidden hierarchy, I mean, you should model that hierarchy into your model. Okay, by doing this, okay, first, okay, you will be able to explain your data much better, and secondly, I mean, also like it has a good impact to the data analysis, as you will see later. Okay, as you will see later. But of course, like the way to model to model a hierarchical model is you try to create like more layers in your model. Okay, we call such a thing as a hyperparameter okay, basically you just try to create more distribution on top of your model parameter, okay, and you can assume those model parameter comes from a shared distribution, okay. So obviously, such approach can be repeated. Okay, I mean, if you want, you can create as many layers as you want in your model. But at the same time, keep in mind like more layers means like it's more complicated. Model is more complicated, and secondly, okay, more layer, okay. If you put like too many layers there, I mean, then it will become difficult for you to explain the result, because after all, the model that you create should reflect, like as I said, like the hidden hierarchy from the data source. For example, like the water example, okay. You collect like data sample, like a water sample from different districts, okay, in Taoyuan City. Yeah, I mean, then it's sufficient to have like a layer for district, okay, and another layer for Taoyuan City, of course, okay. But if you want to go further, okay, can you do that? Yeah, I mean, it's possible, but for example, okay, say now we want to collect like a water sample from the whole Taiwan, okay, because Taiwan has many cities, right? So again, you see a hierarchy which consists of like more than 2 layers, okay? In that case, yes, you could go, more than, more layers. I mean, if it's necessary, but if it's not necessary, okay, you shouldn't do that, okay? This is the concept, okay? The model should reflect the hidden hierarchy in the data. Okay, so this is the water quality example. So so this is first, this data set is synthesized. Okay, the reason we synthesize this data set is just so that we can control it to let you see certain impact of this hierarchical model. Okay, so that's the first thing. The second thing is that, okay, this data set is simplified in the sense that, okay, we try to measure the lead content in the water. You guys know, like, the water cannot contain lead. Okay, if the water contains lead, I mean, it's going to make you stupid. Okay, actually, like nowadays, like in the household we use what's going on? Okay, in a household, okay, we normally use you see like water pipes are made of like PVC, right? Like a plastic, right? So it's actually better for health, because like plastic material does not like leak like harmful material to the water. Okay, but back to like 1 generation ago, like maybe like 30, 40 years ago, okay, it is very common for households, in not only household but also like the community, to use like a lead to construct like water pipes. Okay, why lead? Okay, because you know lead is first, lead is a metal, right? So it's durable. And the second, because lead is softer, right? It's much softer than some. I mean, the other like a metal material. So it can be bent much more easier. Okay, so you know people use lead to construct water pipes. Okay, at that time, people, we didn't notice like lead pipes can release harmful elements to the water. Okay, so actually, it was not discovered until like maybe like a recent 20, 30 years that lead has a bad impact to human. Okay, so it shouldn't be used for the water pipes, and in fact, like the change of this water pipe, you know, is done normally by the government, and it actually, you know, happens like a small region. I mean, after a small region. Okay, so and also obviously, if an area, okay, is is newer, then the chance of having lead pipes is lower. Okay, but if you go to some like a very old community, like in Taiwan, especially in like a rural area, it is still possible you see like a lead water pipes. Okay, which actually are not good for health. Okay, so here, okay, I mean, what we are doing is we are measuring the lead content in the water. Okay, so according to like the WHO, okay, we, you know, as I said, we should the water shouldn't contain lead. Okay, but supposedly the measurement, should be a numerical result, right? For example, like okay, how many ppms, okay, something like that. But okay, here again we simplify the result a little bit. Okay, we just say, okay, we mark one result to be 0. Okay, if the lead content, okay, is below recommendation. Mark with let me see. Okay, it's above recommendation. We mark it with 0. Okay, so it's 0 means bad. Okay, because 0 just means we have more lead content in the water than it is allowed. Okay, and the 1 means we have like lead content below the recommendation value. Okay, so which is good. Okay, so basically, so 1 is good, 0 is bad. Okay, this obviously is a simplification, as I said. Like supposedly the measured result should be a continuous value, right? But just bear with us. We simplified it just so that we can manipulate this synthesized result to show you, to demonstrate like the property of the hierarchical model. Okay, so this is like we generate the synthetic data, okay, with this code. Okay, N sample is 30, 30, 30. G sample is 18, 18, 18. Okay, so we generate this by using like basically what the n sample mean. Oh, here it represents 3 districts. Okay, we have 3 different areas. Okay, and in each area we have 30 samples. So n samples just means the number of samples. Okay, and the g samples just means the number of samples that are good. Okay, so that's hopefully like a very easy to explain, right? So so obviously you need to repeat repeatedly generate some 0 and 1s, okay, in the sample, okay, in the synthetic data set, okay, in order to use this data set, okay. I will not go into the detail of this piece of code. I mean, it's very easy, okay. It just means we generate some 0 and 1s, okay, such that for those 3 areas, okay, the first area has 30, I mean, all of them has 30 samples, and 18 of them are good. Okay, when we say it's good, we mean it's a 1, right? So we have pretty much 12 0 and 18 1s in each area. Okay? So, one thing I want you to be aware is that, okay, we now have the index for the groups, okay? Remember we have 3 districts, okay? So this data set is like, divided into 3 groups, okay? So this index will be used, okay, later on, okay, in your model. So this is the model, okay? So, which is pretty much similar to the coin problem, okay? The only difference is that, okay, in the coin problem, okay, above here, okay, so, I mean, let's try, I mean, omit the top 4 lines, okay? The alpha I and the, first, we don't have I here, the index I, okay? The reason to having, I mean, index I is because we have like groups, okay? We have 3 groups, right? So, secondly, okay, in the coin flip example, okay, the alpha and the beta are directly drawn from a distribution, but the distribution is fixed. Like the parameter for that, the distribution where we got the alpha and the beta will be fixed. But here, okay, you can see that, okay, we don't get alpha I and beta I directly. Okay, what we do is like, okay, we get alpha and beta indirectly from the mu, which is the average, the mean. Okay, so we get the mean and the kappa, which is the concentration, if you remember. Okay, we talk about mean and the concentration. Okay, the beta distribution can be determined, okay, by several ways, right? One is you give like the alpha and the beta value. That's obviously like one way, and the other way is like you are given the mean and the standard and the kappa. Okay, well, kappa in some sense is like is the opposite of standard deviation, right? In some sense, of course, it's not exactly, but when kappa is big, it's more concentrated, right? Okay, the beta distribution is more concentrated. Okay, And when kappa is small, it's more, what should I say, like flat, right? The distribution is more flat. So the impact of the kappa, is exactly opposite of the standard deviation. Okay, because for standard deviation, the smaller it is, like the more concentrated it is, right? So it's opposite. Okay, but anyway, okay. So once you get the mu and the kappa, okay, then alpha can be expressed as like the multiplication of mu and the kappa, and the beta can be expressed as like 1 minus mu multiplied by kappa. Okay, I think I provided at least like formulas, to you guys, like, early on when we talk about the beta distribution, right? Okay, so the reason to not to use alpha and beta, but to use mean and the kappa to determine the beta distribution is because it is more intuitive, because mu is where the middle point is, right? Because, well, it's more intuitive. And the kappa, again, it represents like how dispersed, how concentrated, okay, your distribution is. Okay, so both of these concepts are much more intuitive than the value alpha and beta, right? Remember, like as I said, like when in the coin flip example, okay, if you use coin flip example, if you remember, I told you like alpha and beta can represent like in the trials, how many of them are head and how many of them are tail. Remember? I told you about that. Okay, for example, if you have like 10 trials, and out of these 10 trials, say you have 7 head and 3 tails, then the beta distribution you should use is beta 7 and 3, right? I told you about that earlier, okay, in a coin flip example. But unfortunately, here is not a coin flip. This is a water quality, right? So water quality, in terms of water quality, it's not that straightforward to give the meaning to alpha and beta. So we just use like a mean and the kappa, okay, the concentration, and then okay, with that, the mean and the kappa to come from different distribution. So this is the extra layer that we didn't have. Okay, previously we just assigned values here. Okay, and theta just drawn from like a beta distribution with a fixed alpha and beta value. Okay, and that's it. And from theta we get. Oh, by the way. Yeah, let me finish this part first, okay? So mu comes from a beta distribution. It's sampled from a beta distribution with alpha mu, beta mu. So this alpha mu and beta mu, of course, again, represent certain prior to it, okay? And for kappa, okay, because kappa is has to be greater than 0, okay, and it has, so we set it to be like a half normal, okay, with a mean 0, and well, the mean 0 just means like it's starting from 0, okay, it's a half of the normal distribution, starting from 0, and with like a standard deviation sigma k. Sigma kappa, okay, and then, okay, if you represent this model in like a Kruspe diagram, it looks like this. So this one, from this you can see that, okay, we have a hyper parameters. Okay, or you can say, I mean, if you look at the number of layers, previously we have only 2 layers. Now, okay, we have more than 2. We have 3 layers. Okay, so that's the first thing. Okay, the second thing is that, okay, now, okay, previously, I mean, for example, if we have like a alpha I, beta I, okay, these value actually are sampled directly from some distribution. But now, okay, you see alpha I is equal to mu kappa. Beta I is equal to 1 minus mu times kappa. Okay, you see an equal sign here. Okay, which is also a new thing. Okay, in the diagram. Okay, but after that, okay, I mean on top of that, okay, of course mu is sampled from this beta distribution, and the kappa, okay, is sampled from this half normal. And obviously, I mean, as I mentioned earlier, okay, we have like the I index I represent like a different district because we have 3 districts. So we have like a alpha I, beta I, theta I, and the yi. Okay. So back to here. Okay. I got an email from a student asked me like, here we use Bernoulli. Okay, I mean some people ask me like, why do we use Bernoulli? Okay, instead of using like a binomial. Okay, you guys know what binomial is, right? Okay, so say, let's go back. Let's revisit like the earlier example, the coin flip. Okay, the coin flip, like I mean, you have say theta represent like the probability that you get head. Okay, the coin flip come up head, and y minus theta means like you get I mean tail. Okay, probability you get a tail. Okay, and say you have like you have thrown this coin n times, and you get like maybe x number of head. Okay, then what the binomial distribution is actually something like this. This is binomial. Okay, and the one that we use is Bernoulli. So what is the difference between binomial and the Bernoulli? Okay, Bernoulli is very similar to this, but it's like this. Oh yeah, n 减 x, n minus x. I'm sorry. So the difference is this term. So let me ask you, which one is more reasonable? Based on your high school math. I'm not asking you like anything, more complicated than high school math. It actually comes to our data set. I mean, when you collect a data set, okay, say you collect, like, remember I said if it's 10 throws and you get 7 head and 3 tails, then your data set will be, for example, okay, head, tail, head, tail, head, tail, head, right? So 3 tails, okay, and with several heads, right? So the reason we have that, we have this, is that, okay, we are able to, rearrange the head and tail in this like 10, in these 10 results, right? It's like if I ask you like okay, I mean for 10 trials, okay, if you have 7 head, 3 tails, give me all the possibilities, I mean the number of arrangement that has such a result, okay, with 7 head, 3 tails. Then from your high school, it's 10. Right? Okay, this actually represent what? Represent like with that 10 trial, okay, 7 head, 3 tails, like you can arrange them so that like I mean, how many of those arrangement you have? Each one is this probability, right? So that's why you multiply this probability with that, right? Right? But in your data collection, if you collect 10 trial, as I said, maybe you just head, tail, head, tail, head. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Let me see. 7, 8. Yeah, something like this. So this is your data, right? You are not collecting a data. Say, oh, the data I collect is 7 head, 3 tail, and it's arbitrary arrangement. No. You get one data, right? In a particular order, right? Right? Even when I say, okay, we get a data set. When I describe data, I say, oh, this is 10 throw with 7 head, 3 tail. But it must come from a certain order, right? It must come from certain order, right? The data that you collect must have a certain order, right? Something like this. Okay, this is one of the possibilities, right? Say the data you collect is like this. And I say, oh, it's a 7 head, 3 tails, right? So this is one of the arrangement only, right? Only one arrangement, right? So that's why, okay, you shouldn't multiply that, C10 7 actually, okay, in here, because this is just this is the data you collect, okay. It's not like you collect the data with, okay, all the 7 heads, 3 tails. No. You just collect one arrangement of 7 heads, 3 tails. Okay? Okay, so let me make it clear, okay, why we don't use binomial but use Bernoulli here. Okay? This is the reason. Okay? Just want you to be aware. Okay? So is it clear? Okay, so let's move on. Okay, so with this, hierarchical model, okay, yeah, I think I already explained. Okay, the reason, okay, not to use like alpha and beta from distribution. Instead, we use like mu and the kappa. Two reasons. First, I mean, it is because it's it's faster, okay, in terms of sampling, okay. But this is something has something to do with like the inference engine, okay, which won't be covered until chapter 8, okay, the PyMC3, okay, the inner working of the PyMC3, okay. But you don't need to worry about that. The second reason is, as I said, like I already explained, like the mu and the kappa are more intuitive, okay, to us, okay. So this is like the code for this model. I mean, should be relatively easy to understand, okay, because it's just a direct translation of the model that we just you guys just saw, okay, in the diagram, okay. And then again we use like sample, okay, and we try to generate 2,000 number of samples from for each chain, okay, and we save that in a trace H, and then we plot this trace H. And one thing, I mean, I want you to be aware is that, okay, remember I told you, I mean, when we generate data, the group index, okay, you can see we use the group index here, okay, and I want you to be aware when, I also want you to be aware. Here, okay, I told you we have 3 districts, right? 3 districts, okay? So the alpha I, beta I, okay, this I, we have 3 indexes, right? But, okay, I mean each assignment of the index will be able to allow us to draw a theta I, okay? However, okay, we only have 3, all these alpha I, beta I, all these 3 groups, okay, are sampled from the upper layer. They are all sampled from the upper layer. So in some sense, this one, the top one, the top distribution will be shared by 3 districts, okay? Will be shared, okay? So it is very important, I want you to be aware, okay? The top one do not have index, right? These top 2 distributions do not have index, right? What we have, the index, are this one. And they represent, I mean, it means like for different groups, we have different values here, okay? For example, group 1, we sample the mu and the kappa, and so to create the alpha I, beta I, and from there we sample theta, well, the first theta, okay, and so on, okay? But they all come, eventually they all come from the same, upper layer, okay? So this is a result, okay? You should be able to see something interesting. By the way, I've also forgot one thing. I'm sorry, okay? You see, we create a variable called beta equal to, alpha equal to mu times kappa, and the beta equal to this one. You could put this formula outside or inside like this. Okay. Normally, okay, when you see a variable like this, these variables are sampled from distribution. That equal sign means they are sampled from the distribution. But this one is not. Okay, this one is not. Okay, this one means, okay, mu times k is alpha. Okay, just a regular equal sign that we use in the programming. Okay, so these two, I mean, even though you see mu, kappa, theta, y, okay, and alpha, they look, okay, to you. They may look to you. They are just all variables, but they have different properties. Okay, the mu, kappa, theta, y, okay, are more like what's the name? It indicates it's a sample from a distribution. It's a what's the English name for that? I suddenly forgot. But anyway, okay, we will talk about that. We should be able to talk about that later. Okay, and then okay, so you see we have a mu, we have kappa, okay, and the mu kappa that comes from the top distribution, okay, and then okay, we have 3 theta, okay, theta 0, theta 1, and theta 2, because we sample the theta for 3 different districts, right? And the result, are here, okay. And it shouldn't be a surprise to you because these 3 districts have almost has identical result, right? Out of 30 trials, we have 18 good samples, right? So if you look at statistic, these results, the summary of the statistics, you will find that, okay, well, out of 30, we have 18 good samples. So what is the probability that this, if you compute average, it's 0.6, right? Okay, 0.6. That's why you see it's peak at 0.6, right? Okay. So nothing is surprising, okay, so far. Okay, even though we use the hierarchical model, but what happened next is we want to show you something interesting. But well, if you have a computer, you can try to run the code, okay, with PyMC3 yourself, and you can adjust the group, the good sample number for each group, okay. So it is suggest that the first one you just try to set all the elements of G sample to 18. Okay, the second one is to set all the elements of G sample to 3. So the previous is where is it? Okay, the first one is like this. The second one is like this 18, 18, 18. Change that to 3, 3, 3. So you only have 3 good results, okay, from all 30 samples. For each district, okay, and you can guess. You can do a wild guess. Okay, what is the result? Okay, because they are all identical, right? So pretty much well, they should give you again the similar distribution, right, for each group. And if you do a simple calculation, you can guess the I mean, the peak should be close to 0.1, right? Okay, it's going to be slightly moving to the right because keep in mind, okay, we are talking about beta distribution, which is only defined, I mean, inside, I mean, the 0 and 1, right? So it's going to be a little bit, okay, so it's if it's moving a little bit to the right, at least it should be very close to 0.1. Okay, the third one is so that's where am I? Okay, the third one, the third trial of the same example is to set the first district to 18 and the second and the third district to 3. This is where it gets interesting. Why? Because from the previous 2 rounds, we know, okay, if a district has like 18 good sample, okay, the peak should appear somewhere around like 0.6, right? And if the district has like only 3 good samples, then the peak should be around like 0.1, right? But if you try to put this into your data set and try to generate it and try to run this hierarchical model, what is going to happen? Okay, you see, this is the result. Okay, 18, 18, 18 is 0.6, 0.6, 0.6. 3, 3, 3 is 0.11, 0.11, 0.1. Of course, if you run it, it may be slightly different. Okay, after all, we are talking about probabilistic programming, right? But it should be very close. Okay, well, because the random seed may be different. Okay, but it should be maybe 0.6 something, but it's very close to 0.6. Okay, something like that. So it's, again, I mean, it could be 0.11 something, but it should be close to 0.1 in certain, you know, a certain degree. But so these 2 are not surprising, as I said. What happened, what is interesting is the third one. The 1833, okay, we would have expected the first one is close to 0.6. The second and the third one should be close to 0.1, right? But you will see something like this. Okay, the first one is not 0.6. It's closer to. I mean, you see, not only this one, but the other 2, they are drawn closer, right? They are drawn closer. They are pulled, I mean, together. Why is that? This, you know, this phenomenon is called shrinkage, and which is a very, very important concept in hierarchical model. Okay. The reason is because, okay, in this model, of course, your data is here, right? The data sits here, right? So, yeah, I mean, you have a prior, right? You have a prior for your alpha mu, beta mu, and also the sigma kappa, right? Those are priors, right? Those are priors. But, okay, as the data comes in, okay, even though the data are divided into groups, but remember what I told you, okay, the top 2 distributions are shared by all these groups, right? So all these groups, the data in all these groups, okay, obviously will have impact to the posterior of these two things, right? They will have impact to the posterior of these two distributions, right? And once the posterior of these two things are somewhat determined, I mean, they will have impact to after you draw, different value of, different distribution to generate like the theta I, right? For different groups. Okay, so this group, okay, this theta I, okay, is not only affected by, you know, the data in one group. It somehow also gets affected by, well, I could say remotely, okay, from like the impact of other group through the top distributions. Okay, so the data actually, even though, as I said, even though the data may have different groups, okay, as long as they share the parent distribution, okay, then the data in the other groups will affect the result of this group. Okay, that's the concept of shrinkage. That's the concept of shrinkage. So that is why, okay, yeah, the 0.6, originally 0.6 for the first group, okay, they got impacted from the other groups. So they move a little bit closer to a smaller value. And the same thing happens for the second and the third group. Okay, they get impact from the first group, so they move a little bit bigger. They are pulled, to become bigger. Okay? So this is like a special property of the hierarchical model. Okay, of course you may argue, okay, well, yeah, that's, yeah, well, it's time, for a break. Let's take 10 minutes break. When we come back, we'll continue to discuss like why shrinkage. Is this phenomenon, okay, reasonable or not? Okay, we'll talk about this shortly, okay?